Welcome to our next video in the series on condensed matter theory. In this video I want to talk about the band structure that we find in materials, and we do this in the Sommerfeld model for a start, so the free electron model. The band structure in the free electron model is a relatively simple function, but this concept will be very useful also later in the lecture. And we will talk a lot about electronic band structures, also related to Green's functions. So, what is a band structure? You have seen in the previous video that we can talk about the one particle energy as a function of momentum or wave vector as h bar squared k squared over 2m. And these are the one particle eigenfunctions of our system. This allows us to draw a diagram where on the horizontal axis we put momentum and on the vertical axis we put the energy. Now, of course, the momentum is a variable in 3 dimensions, so let's first make a plot in 1 dimension. Well, in 1 dimension this is just a parabola. And we have seen that we can define a Fermi energy and a Fermi wave vector, Kf, and all states below the Fermi wave vector are occupied and all states above the Fermi wave vector are empty. Then, of course, we have this energy momentum dispersion relation, so with this Fermi wave vector comes a Fermi energy, EF. The states that we have are discrete in terms of wave vector because we put our states in a box, and they're equidistant spaced in momentum. So we have below the Fermi wave vector occupied states and above the Fermi wave vector empty states. We have n states below EF or below KF, and of course infinitely many above. The spacing between 2 states is equidistant in momentum and given by 2 pi divided by L. And in the end we will take the limit of L to infinite, but as properties are normally extensive, we will see that the volume or the size, the dimensions of your system will drop out. In 2 dimensions, this of course becomes a 3-dimensional plot where we can look at Kx and Ky, and then this is a parabola in 3 dimensions, and these form spheroids, and this is a surface of allowed states, and then these states are actually points on that surface. We will find ways to not have to plot 2-dimensional figures or 3-dimensional figures, and when you go to 3-dimensional space, even 4-dimensional figures, but we will look at certain paths through momentum space to represent what we have here, our energy momentum dispersion. When we go and include the crystal lattices, we will find that the band structure will become more involved as we have here, and that's why it's going to be a very important concept to talk about the energy dispersion relations of the electrons that we have in our system. For now, in the Drude model you have this quadratic dispersion, and that's the band structure of our electrons in the Sommerfeld model. Thank you very much for your attention, and this was a shorter video. We'll see each other in the next video. Stay healthy.